Welcome everyone. With this video, we are starting Calculus 2. We will talk about integrals and antiderivatives. Before talking about integral, I have book recommendations for those who want to self-study as well. Howard Denton Calculus, James Stewart Calculus. Howard Denton is my personal favorite. And Shahum Problems, that includes 3,000 problems. This book is also really good for studying, exercising, solving some problems maybe. But as I said, Howard Denton is my personal favorite. Alright, let's start with definition of antiderivative. If f prime of x is equal to f of x, what do we mean? Of course, the first derivative of f of x from calculus 1, then f is called an antiderivative of f. The definition is pretty straightforward. What I want to do is to find an antiderivative, I will reverse the differentiating step. So for example, f of x is equal to 2x, find antiderivatives of it. For example, x squared. Why? Because when I differentiate this function, it is equal to my original function. But it says antiderivatives. Why? Because I could also write x squared plus 1, x squared plus 2. And I have infinite amount of these constants, right? Let's see a theorem related to this. If f prime of x is equal to f of x on the open interval, then every antiderivative g of f on I is of the form g of x is equal to f of x plus c, where c is an arbitrary constant. In other words, the difference between two antiderivatives is a constant. What do we mean? For example, let me name this g of x. I can write g of x is equal to f of x plus 1. If I had another antiderivative for this function, for example, x squared minus 3, I could write g of x is equal to h of x plus 5. So the only difference is the constant we have. And now let's try to prove this. I know I'm starting with a proof, but it's a really simple proof, and I think we need to understand the theorem really well. What do we want to prove? We want to prove that the difference between two antiderivatives is a constant, so we need to show that we can write it in this form. I will start by taking a function. Let's take the function f of x. And now I'm going to take two antiderivatives for f of x. Of course, we are accepting that it's differentiable, blah, blah, blah. Let's assume f of x and g of x are antiderivatives of f of x. What do I mean by this? I mean that when I differentiate these two functions, I get my original function f of x because that's the definition of antiderivative. I differentiate my antiderivatives, I get back to my original function. Now what I want to do is I want to subtract these two derivatives. Minus g prime of x is equal to f of x minus f of x will be equal to 0. F prime of x minus g prime of x will be equal to 0. From calculus 1, I know that. Let's change the color because from calculus 1, I know that if I differentiate a function and it's equal to 0, this is only possible when h of x is equal to a constant. Derivative of a constant is equal to 0. Why do I need to remember this? Because I can write this as h of x minus g of x differentiated is equal to 0. This is also from calculus 1. I get a new function here. So this has to be a constant because of the calculus 1 rule. Therefore, f of x minus g of x has to be a constant, which means f of x can be written as g of x plus c, which proves the theorem. So the only difference between two antiderivatives is a constant. We show that that is true. Definition: let f be the derivative of a function. The class of all antiderivatives of f is called the indefinite integral of the function f with respect to the variable x. Notation for it: this is our integral sign, like this. F of x, the function we are integrating, we call it integrand, and dx is from calculus 1, our differential. According to this definition, if f is an antiderivative of the function f, then you can write it as f of x dx, integral of f of x, can be written as f of x plus c, where c is a constant. And here we have if and only if, also saying the same thing. When you differentiate it, you get to the original function, and when you integrate it, you get to the f of x capital as well. Example, evaluate the given integral. Integral 3x squared dx. What could it be? The question is simple. I need to differentiate a function that I get 3x squared. Obvious, right? If you differentiate x cubed, you get 3x squared. But for the constant, you put a plus c. Don't forget the plus c, because if you have a calculus exam or anything, if you don't add the c, you will see a huge zero on it and you will question why, because you forgot the c. Let's look at some integrals. We can evaluate these integrals because we can find the function that when we differentiate, we get the integrand from calculus 1. For example, x to the m dx, what could it be? X to the power of m plus 1 over m plus 1. Differentiate this, m plus 1 cancels each out, m plus 1 minus 1, m gives me this, right? But I need to be careful, of course, plus c as well. And I need to be careful because m cannot be equal to negative 1, which would make the denominator 0. 1 over x dx, you can write it like this as well, or you could write it as 1 over x dx, which is equal to ln absolute value of x plus c. Integral a to the x dx. A to the x over ln a, because when I differentiate it, this is equal to a to the x ln a. Ln a's will cancel each out, and it will give me the integrand. E to the x, again, is equal to e to the x plus c, because when you differentiate it, it gives itself. When you integrate it, it also gives itself. Sine of x dx. If I try to say it is equal to cosine of x plus c, differentiating cosine of x would give me negative sine x, so I need to add a minus sign here. For cosine of x, sine x plus c. For cosecant x dx, I have negative cot x plus c. Let's continue. What is going on? Let's continue. Secant squared x is equal to clearly tan x plus c. This is equal to arctan of x plus c. Arc sine of x plus c. Our hyperbolic functions, if I differentiate cosine h of x plus c, and if I differentiate sine h of x plus c, sine hx plus c, I get back to my integrands, so these will be my integrals. For these two, you can don't worry about it right now, because some of us did not see this before, but we have other methods to integrate, and we will learn how to integrate these functions as well in the future. X squared minus 1 plus c. Properties of our integrals, it's pretty easy. Our first property tells us that we can take the constant out. Why? It's easy because we're used to these ideas already from derivatives. So this means if I have, for example, integral 3x dx, I can write this as 3 integral x dx. I took 3 out of it. If I have two functions, I can write them as separate integrals. For example, x plus x squared dx is equal to integral x dx plus integral x squared dx. Our last property tells us that we can combine property 1 with property 2. For example, integral 3x plus 6x squared plus 9x cubed dx can be written as 3 integral x dx plus 6 integral x squared dx plus 9 integral x cubed dx. In our examples, we learned a lot already. Now let's try to apply these. We will have to use the properties of integral as well. I will go step by step. Normally, you could probably figure it out just by looking at it, but it's first time doing it, so let's go step by step. First, I'm gonna use property number 2 and separate the integrals. 6x squared dx minus integral 4x dx plus integral 3 dx. I could use property 3 immediately as well, but I want to go step by step. After this example, we can do that as well. Now let's take the constants out. Property 1, 6 integral x squared dx minus 4 integral x dx plus 3 integral dx. From here, 6 by x cubed over 3. Let's write it one more time. Maybe we can forget it. It's okay. Well, you can just find it by logic, but let's have it there. Minus 4x squared over 2 plus 3x plus c. Don't forget the c, right? Let's do the simplifications. These can cancel each out. 2x cubed minus 2x squared plus 3x plus c is my integral. Evaluate the integral. We will do the same thing all the time. We will separate them. 2 sine of x dx plus integral 8 square root of x cubed dx plus integral 5 over x dx. Now I will take the constants out. 2 integral sine of x dx plus 8 integral. Instead of square root of x cubed, because I cannot use the power rule really well here, I will write x to the power of 3 over 2 dx, because I know square root of x is equal to x to the power of 1/2, plus 5 integral 1 over x dx, which is equal to, now we can integrate. And of course, for sine of x, I need negative 2 cosine of x, plus 8, I add 1 to the power, x to the power of 5 over 2, right? 5, yes it is. Now I need to divide it with 5 over 2. Instead of that, let's write 2 over 5 plus 5 ln absolute value of x plus c. Let's do the simplifications. Well, we don't have much. You could write that. Let's do it. Negative 2 cosine of x plus 16 square root of x to the 5th power over 5 plus 5 ln of x plus c. Example 3, if I'm not wrong, we have 3 more. Let me share it actually. Maybe you want to solve it by yourself first. Well, I will add the PDF anyway, right? I forgot that. I do that, right? Okay, I did not upload in some time. We have another integral. What do we do? I'm gonna take the constant out immediately. I'm using property 3 from now on. 1 over cosine squared of x. I don't like seeing this form. I prefer seeing secant squared of x dx. I don't know why. It's completely fine to write it like that, but personal choice. E to the x dx minus 2 integral 1 over 1 plus x squared dx. Alright, 4, if I differentiate tan of x, I get secant squared of x, tan of x, plus 3 e to the x, minus 2, what do I have here? Arc tan of x, plus c. We did differentiate these in the previous videos, you can check it out from there. As I said, I don't know if I said, I have other plans for Calculus 1. I might even make the entire series from zero. I don't know. I did not like the way I did it, so I'm thinking of working on it. I don't know how am I gonna do it. I will figure it out. I'm not in a hurry or anything, so. Okay, let's look at this integral. Of course, I cannot work with this, obviously, what am I? Well, this part is pretty simple, right? Because integral 2 over 1 plus x squared dx is equal to 2 ln x plus 1 plus x squared. We showed this. This was plus c, of course. We showed this in number 14, I think, or 13. I don't know. 13. This part is easy, but what about this part? So first of all, I will write these as separate fractions. 5x squared over square root of x dx minus, let's take the 5 out, so why not? 6 integral x over square root of x dx plus 3 integral 1 over square root of x dx plus, I don't want to write all of this for now. I will say this is equal to a, and I will write plus a, but the c will be a problem. Well, not really. We will write plus c in the end as well. Okay, but still I cannot use the power rule that easily. What am I gonna do? 5 integral x squared by x to the power of negative 1 over 2 minus 6 integral x multiplied by, again, x to the power of negative 1 half. I'm gonna do the same thing for every integral. I have 3 integral x to the power of negative 1 half, 1 and a half e of x dx plus a. Now I can kind of start using the power rule, but one more thing, I need to add the powers, right? 2 minus negative 1 over 2, 3 over 2 minus 6 integral. This is 2, so this is 1 over 2 again, plus 3 integral. I just have negative 1 half here. X plus a. Let's start integrating. Wait, did I do anything wrong? Let me check one more time. Looks correct to me. Now I can add 1 to the power and divide it with the power. 5 x to the power of 5 over 2. This is divided by 5 over 2 as well, so I will write 2 over 5 minus 6 by x to the power of 3 over 2 by 2 over 3 plus, I'm just writing the fractions like this instead of writing a division, so the numerator and the denominator change the place. 3 x to the power of 1 half multiplied by 2, right? Yes, really good. Plus, I'm gonna write a one more time. This includes c as well, so I will leave it like this for now. This is equal to, let's do some simplifications, 2 to the power 2x to the power of 5 over 2 minus 6 to a negative 4x to the power of 3 over 2 plus 6x square root of x plus, instead of a now we write 2 ln x plus square root 1 plus x squared plus c. I hope we did not make any algebraic mistakes, but it's okay. You can figure those out by yourself. Example number 5. Is it last one? No, we have 6. Okay. Example number 5. I start with separating the functions d of x plus 6 integral e to the x dx plus 4 integral. I don't like seeing 1 over sine squared x. I will write cosecant squared of x d of dx plus integral x cubed dx. Now it's pretty easy. 3 cosine hx plus 6 e to the x plus minus, because now I get negative cot x, 4 cot of x plus x to the 4th power over 4. I add a plus c. This is my answer. Our last example, it's a really simple one. I will separate this as well. X to the 4th power dx plus integral 4 to the power of x dx. Left side is equal to x to the 5th power over 5 plus, now right side, 4 to the power of x over ln 4, because when I differentiate this, I need to get back to the integrand. This is my integrand, plus c.